Hey folks, my name is Cole and this is the 8th video in the UP1 final exam study guide, and we're going to be talking about work. So work is denoted by a capital W, has units joules, which are the units of energy, and 1 joule is 1 kilogram meter squared per second squared in SI units. So what is work? Well, we've talked about like forces acting on objects, but work is a measure of actually how much a force contributes to the motion or the displacement of an object. So it's going to depend both on the force that you're exerting on the object and also how much the object is displaced. So the equation for work by a constant force is that work is equal to the force dot the displacement, which we're going to denote with an R to indicate that it could be in any direction. It's just some radius vector. And that's the equation. That's the equation for work done by a constant force. So let's think about this. We can see both that if the displacement is higher and if the force is higher, that the work done by that force increases. But we also see this dot product here, which we talked about recently. And that dot product tells us something really important about the work done by a certain force. If I have an object like a box and I am pushing it along a floor so that it ends up here, a couple meters away, and I'm pushing on it downwards, kind of at an angle like this, maybe at a 30-degree angle. Not all of this force vector F contributes to the displacement of the object, right? Because we have this dot product here. Not all of it is doing work on the object. Only the component that contributes in the dot product is doing work. Which component is that? Well, if you remember, a dot product A dot B is equal to the magnitude of A times the magnitude of B cosine theta, where theta is the angle between A and B. So in this case, we can rewrite work as W is FR cosine theta. Okay? So if we look here, the displacement is in the positive x direction. So our cosine of theta is going to be this component of the force, this horizontal component, right? This vertical component actually does no work. And this makes a lot of sense, because imagine for a minute if I were to push down vertically on the box. I would be exerting a force, maybe a whole bunch of force, maybe like 1,000,000 newtons of force, but the box would never move because the ground would just push right back up on the box with the same amount of force that I was pushing down on it. So the only component of a force that can cause an object to move, that can do work on the object, is a force that is parallel to the displacement of the object. I have to push the box to the right in order to make it go to the right. So this is also going to be really helpful for us when we're talking about the summation of forces. You'll notice that the summation of work, I should say. You'll notice that work is a scalar. It's energy. Energy is always scalar. And this is super nice because if we're looking for the net force on an object, which we might want to find later when we talk about kinetic energy a little bit, all we have to do is sum up the summation of the work done by every single force on the object. We don't have to care or worry about any vector addition. And it also means that if I have an object that's moving to the left, or to the right, for example, that is a right-facing arrow that I've just drawn, how much work is the gravity doing? Well, the gravity is perpendicular to the displacement. Any vector force perpendicular to the displacement, it has a cosine 90 in the dot product. Cosine 90 is 0, so this gravity work done by the force of gravity, it's 0. It's going to be really useful. So that's the work done by a constant force, but we have one more thing that we need to talk about, which is what if the force is non-constant? So sometimes you're going to have something exerting a force with a function of either time or like distance. And in these cases, you can't use this dot product formula, and we're going to have to use calculus. We're going to have to integrate. So the very general definition for work that is always true, this calculus definition, is that the work done by a force is equal to the integral from some initial distance to some final distance, so we're integrating with respect to a distance, of force dot dr, okay? And the r is also a vector, that's the displacement vector. So it's very similar to this equation for a constant force, but we have this dot product inside of an integral, and that's something that's a little bit messy. I personally don't really know off the top of my head like how to integrate a dot product inside of an integral. It's a little bit messy. But what I do know is the definition of dot product, the component definition of dot product that we went over in one of the previous videos. And that's that if I have a vector, for example, f, with components fx, fy, and a vector r with components rx, ry, well, the dot product f dot r is just equal to fx rx plus fy ry. Okay, that's the component definition of dot product. So what we can actually do when we have a non-constant force is, even though this is the general definition, it doesn't really help us because we don't know how to integrate this. We have to split it up. We have to split up work, or force, I should say, into its components. So this becomes that the work is equal to the integral from some initial x to some final x of the force in the x direction times the displacement in the x direction, which I'm going to actually denote as dx. Because at this point, x is just a direction, it's a distance. So fx dx plus, because remember, work is additive. It's not a vector. We can just add it all up. The integral from some initial y to some final y of the force in the y direction times the displacement in the y direction, plus, if we have a z direction, force in the z direction times dz, dot, 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 right? You could do this for any number of dimensions that you could possibly want. And this is the equation that's going to be useful if you are given the component of a force vector and the component of a displacement vector for a non-constant force. All right, so this is all I have for work. Work is going to be really important when we start talking about more about energy, because we're going to have to find like the loss of energy in a system due to work done by external forces, and we're also going to talk about how work relates to kinetic energy and potential energy and how we can use that to our advantage solving systems. So before I go, I just want to point out where work is on the formula sheet. You can see the work done by a constant force here is F dot, they've put a delta here, but it's the same thing, F dot R. And then the general equation is this calculus definition here, F dot dr integral, or you can break it up into its vector components. So it's all there on the formula sheet under what I've labeled say. All right, next time we are going to start talking about kinetic energy, and then we can relate the two with the work kinetic energy theorem.